Hello everyone, my name is Austin Leeds. I am a graduate research associate in the Conservation and Science Division of Cleveland Metroparks Zoo and a PhD candidate in biology at Case Western Reserve University. I am excited to have the opportunity to share with you a recent study that I published along with Dr. Kristen and Lukas on self-directed behavior in mandrills. For reference, our paper is titled Experimentally Evaluating the Function of Self-Directed Behavior in Two Adult Mandrills, Mandrillus sphinx, and was published in the February issue of Animal Welfare. One of our study participants, Linus, was also featured on the cover of the journal. Optimizing the welfare of animals in zoos is of utmost importance for zoo professionals. Assessing animal welfare through behavioral observation is a common practice and requires the identification of behaviors that can indicate both positive and negative welfare. However, identifying and validating how specific behaviors relate to an animal's welfare state is challenging. Self-directed behavior, which includes behaviors such as self-scratching, yawning, and body shaking, has long been considered a behavioral indicator of stress in non-human primates, and thus may be a useful tool in assessing an animal's welfare state. This hypothesis has been supported by studies that have demonstrated rates of self-directed behavior increase following social conflict, when the spatial density of groups increase, and following the administration of anxiogenic or anxiety-inducing drugs. These are just a few highlights of the research that have contributed to our understanding of self-directed behavior as it relates to stress. Interestingly, there is a growing body of research demonstrating that this relationship may not be as straightforward as we once thought. For example, in both Hamadryas baboons and all baboons, no correlation has been found between salivary cortisol, a physiological measure of stress, and self-scratching. Interestingly, in a recent study of marmosets, self-scratching was observed to increase during play, a behavioral indicator of a more positive emotional state rather than a negative emotional state. And also recently, a study of free-living Japanese macaques reported that lice density was a better predictor of self-scratching than social stress. This research collectively shows us that self-directed behavior can be used as an indicator of stress. However, it may not be a universal indicator of stress depending on the species and context. Those seeking to utilize it as a measure of welfare should ensure that the behavior has been validated as a measure of stress in their respective species of interest. At Cleveland Metroparks Zoo, we were interested in validating self-directed behavior as a measure of stress in mandrills so that we could include it as part of our behavioral monitoring program for the species. Like the study of self-directed behavior in other species, the literature on mandrills is mixed. Shino and Marini found that self-scratching increased following agonistic encounters, and Payneau et al. Reported that during feeding tests, there was no increase in rates of self-scratching compared to pre-feeding periods, despite noting there was an observed tension within the study groups. It is also worth noting that neither study reported on rates of yawning or body shaking. Self-directed behaviors common in other primate species, and behaviors that are also often listed in ethograms in the study of mandrills. At Zoo, we initiated a touchscreen cognition program with our two adult male mandrills. Previous research on self-directed behavior used in primates have used cognitive testing as a way to validate the function of self-directed behavior in relation to stress, and we sought to use our touchscreen-mediated cognitive test as a way to study self-directed behavior in our two mandrills. Particularly, we modeled our study after a study conducted by Wagner et al. At the Lincoln Park Zoo. We hypothesized that if self-directed behavior is a behavioral indicator of stress in mandrills, the mandrill's rate of self-directed behavior will increase with task difficulty, given that an increase in cognitive challenge may increase the cognitive stress perceived, and be greater during incorrect compared to correct trials, given that incorrect trials are associated with uncertainty of not being able to successfully complete the trial, as well as three negative stimuli: not receiving a food reward, a harsh tone played alongside a harsh white screen, and having a timeout before being allowed to attempt the next trial. Our study participants were two adult male mandrills, Linus and Woody, who live at Cleveland Metroparks Zoo as a bachelor group. The mandrills were participating in a list sequencing task where they were challenged with learning to list random symbols in a predetermined order. For reference, this is a video of Linus completing a 5-item list. The touchscreen is placed flush with the mesh, and a mirror image of the screen is viewable on the laptop screen. Each day of testing, the mandrills are provided the opportunity to complete up to 40 trials if they chose to. The mandrills were filmed on random testing days to assess their self-directed behavior use, with a total of 30 testing sessions filmed for each subject. We coded the rates of self-directed behavior from video and calculated the rate of each behavior per second of trial length. During the study, we recorded 3 self-directed behaviors, the first of which was self-scratching, you can see demonstrated here by Linus, here by Woody, and then one more time by Linus. We also recorded yawning, which will be demonstrated here by Linus. And body shaking, again demonstrated here by Linus, followed by Woody. We compared rates of these self-directed behaviors in two ways. The first context was task difficulty. We filmed 10 testing sessions for each of the following task difficulties for each subject and compared self-directed behavior use between each task difficulty. The easy task was a 2-item list with a 50% probability of successfully completing each trial. The medium task was a 3-item list with a 16.5% probability of successfully completing each trial. And the hard task was a 4-item list with a 4.1% probability of successfully completing each trial. The second comparison was the use of self-directed behavior between correct and incorrect trials. For these, we combined all task difficulties, and you will see why we did that on the next slide. This graph shows the rates of each self-directed behavior by subject by task difficulty. And you can see we saw no significant difference in the rate of each behavior by task difficulty. Interestingly, a similar result was found by Wagner et al.'s study of self-directed behavior in chimpanzees and gorillas. As a result of this finding, we compiled the data across task difficulty when comparing correct and incorrect trials. When comparing rates of self-directed behavior between correct and incorrect trials, we found several significant differences. For both subjects, rates of self-scratching were significantly greater during incorrect trials compared to correct trials. We also saw individual differences. For Linus, his rate of yawning was significantly greater during incorrect compared to correct trials, but no difference was found between rates of his body shakes. For Woody, rates of body shakes were significantly greater during incorrect compared to correct trials, but no difference was observed for rates of yawnings. In fact, yawning was never observed during testing for Woody. The purpose of this study was to experimentally test the function of self-directed behavior in mandrills using a touchscreen-mediated cognitive task. Our first hypothesis predicted that self-directed behavior would increase with task difficulty. Our results did not support this hypothesis, which is surprising given the difference in probability of successfully completing a trial as task difficulty increases. However, a similar outcome was reported by Wagner et al., who evaluated the use of self-directed behavior in gorillas and chimpanzees at the Lincoln Park Zoo. This may indicate that the rate of self-directed behavior does not correlate with the perceived level of stress, but rather a minimum threshold of perceived stress elicits self-directed behavior. Alternatively, although each task was significantly more challenging, the mandrills might not have perceived the tasks as being more challenging despite the difference in percentage of correct and incorrect trials. It is also worth noting that the potential stress of not receiving a food reward could be greater than any increase in stress by task difficulty, resulting in the same level of perceived stress across testing conditions as long as incorrect trials occurred. Our second hypothesis predicted that self-directed behavior would be more frequent during incorrect compared to correct trials. This hypothesis was supported by the data as well as data from a similar study of ape self-directed behavior. Self-scratching was greater in both subjects during incorrect trials, which provides support that this behavior is an indicator of stress since it was associated with uncertainty following an unsuccessful trial, and as well as 3 negative stimuli: not receiving a food reward, a white screen flash accompanied by a harsh tone, and a timeout before being allowed to complete the next trial. This also provides evidence that this behavior is not an indicator of positive arousal, as has been observed in other species, since rates were low following a correct trial where a food reward was provided, as well as positive verbal encouragement from the researcher. The individual differences in specific self-directed behavior use were also noteworthy, and further support other studies that argue welfare should be measured at the individual level. Future studies examining self-directed behavior should evaluate individual behavior use by subject to ensure that each behavior is meaningful for each subject. It should also be noted that this study included only 2 subjects, so applying the results beyond this group are difficult, but this data further supports research conducted by Shino and Marini that self-scratching can be an indicator of stress in mandrills. Further research is needed to fully validate these behavioral indicators of stress in mandrills, as well as in other species. We hope that other researchers conducting cognitive research with primates can use the ongoing test as an opportunity to assess these behaviors in their respective subjects and study species. I appreciate you taking the time to listen to this presentation. I would like to thank Dr. Grace Fuller and ASP for providing me this opportunity to share my research with you. I would also like to thank Avery Zhu, Claire Thiel, Caitlin Gaffney, Julie Good, Dr. Lana Les, and Tad Schaffner with their assistance with this project. In addition, we would like to thank Dr. Christopher Kuhar and the Cleveland Zoological Society for supporting the Mandrill Research Program at Cleveland Metroparks Zoo, and to Dr. Steve Ross for providing the cognitive software used in this study.